Find the absolute maximum and minimum values of f of x equal to x to the 2/3 on the interval from -2 to 3. We get the first derivative, and then set it equal to 0 to find the critical points. So we've got f of x equal to x to the 2/3. What's the first derivative? F prime of x is equal to, drop down 2/3, and then x to the -1/3, and then that's of course taking off negative or adding -1 to 2/3, you got a -3, and then just bring down the x to the 1/3, set that equal to 0. The numerator will not become 0, but the denominator will be 0, which will make the derivative undefined. That's when x is equal to 0, right? So that becomes our critical point. Remember, a critical point is what makes the first derivative either 0 or undefined. And now all we do is compare the endpoints with the critical point as well. So we evaluate at f equal to -2, f at 0, and f at 3. F of -2 is just -2 raised to the 2/3. Then f of 0 is of course just 0, because 0 to the 2/3 is 0. Now what is f of -2? That's the cube root of 4, because you know -2 is squared, and then we take its cube root. What about f of 3? f of 3 is 3 squared, and then you take the cube root. So that's 3 to the 2/3 makes it the cube root of 9. And all we do now is compare all these 3 points, and of course f of 0 equal to 0 becomes the absolute minimum, that's the smallest value, and f of 3 is the absolute maximum. Alright, here is the graph of the function y is equal to x to the 2/3. And if you see, there is a line tangent to the curve at x equal to 0, that's where the critical point occurred. And remember, it was undefined because the line tangent is vertical, so the slope is undefined. And that's where the minimum occurred at the origin, and then the absolute maximum occurred at x equal to 3, right there. Here's another exercise, set of exercises finding extreme values based on the graph. And we will decide whether we can find the extreme values on the closed interval and explain why it's consistent with Theorem 1. Right, so what are the conditions that Theorem 1 assumes? We have a continuous function on a closed interval, which means we'll be able to get an absolute maximum or minimum. Here, the absolute minimum occurs at an interior point at C2, so that's our absolute minimum. Then, at B, which is an endpoint, that's where the absolute maximum occurs, right there. Now let's turn to number 2. Okay, we see that there is absolute maximum occurring at x equal to c. There is our absolute maximum. And then at B, at the endpoint B, we attain an absolute minimum. Now what about 3 and 4? We have an endpoint, we have an open interval from A to B, so we don't even attain an absolute minimum here because we've got an open interval as our domain from A to B. And Theorem 1 assumes that we're supposed to have a closed interval. It is a continuous function, but we've got an open interval. However, we can attain its absolute maximum at C because it's continuous, and that's the maximum value right there. Right. What about in number 4? Again, we've got an open interval from A up to B, but here in the interior of A to B, the function is discontinuous at x equal to C. Discontinuous at x equal to C. So it did not even attain an absolute minimum because of the discontinuity of h of x in the interior. In particular, we have an open hole occurring at x equal to C. Example, exercises 7 to 10. These are your homework problems that you can work out to find the extreme values. Find the absolute maximum and minimum values of h of x equal to the cube root of x on the interval from -1 to 8. Then we graph and then find the extreme values. First, get the derivative. We take h of x equal to, write it in power form or exponential form, so it's x to the 1/3. Take the first derivative, drop down 1/3, then x to the -2/3. That's the same as 1/3 x to the 2/3. Set it equal to 0, and it's never 0, but it will be undefined when x is equal to 0. So that gives us a critical point at x equal to 0. Now let's evaluate at the critical points, and critical point and the end point. So the cube root of -1 is -1. The cube root of 0 is, of course, 0. And then the cube root of 8, that's h of 8, the cube root of 8 is, of course, equal to 2. So we've attained our absolute minimum when x is equal to -1, and the absolute maximum occurs when x is equal to 2. Now let's plot the points so that we can graph and see that that's how the graph looks like from -1 to 8. There's the absolute minimum and the absolute maximum. And then where the critical point occurred at the origin is when the slope of the line tangent to the curve is undefined. You've got a vertical line that's tangent to the cubic function. And that's where the critical point occurs. Exercise 27. We have a function f in terms of theta. So f of theta is equal to the trig function sine theta. And we are confined in the interval from -π/2 to π/2. What's the first derivative? It's cosine of theta. Set that equal to 0 to get the critical points. Now, what are the angles that make cosine theta equal to 0? Go back to your unit circle, and it's a quadrantal angle that either falls on a 90-degree angle or a -90-degree angle. So that's when it's π/2, -π/2, 3π/2, etc. That means whenever k is odd. So any odd multiple of π/2 makes the cosine equal to 0. But we have to confine the angle where it's contained in that closed interval from -π/2 to 5π/6. So what are those angles? Well, let's go ahead and plot first where is -π/2 on the number line. Okay, that's 0. That's π/2. And then pi. So we graph the function from negative pi over 2 to 5 pi over 6. So where is 5 pi over 6? You just divide pi into 6 parts and take the fifth one to get the endpoint, the right endpoint. And there's 5 pi over 6. So we take the angles minus pi over 2 because it's contained in the closed interval, and of course pi over 2. So these are the only two critical points that are contained in the closed interval. Now let's find the y values at the endpoints, which also turns out to be the critical point. The coordinates here on the unit circle are 0, negative 1, and 0, 1. That's when the angle is pi over 2. So the sine of negative pi over 2 is negative 1. The sine of pi over 2, which is a 90-degree angle, is 1. Now let's evaluate the sine of 5 pi over 6 because that's the other endpoint. And the sine of 5 pi over 6 on the unit circle, that's on the second quadrant, and it's the 30-degree angle, so the sine is 1/2. So now you compare all these three values of the sine and just find our absolute minimum as our smallest value. It's when the angle, or x, or rather theta, is minus pi over 2, and the maximum occurs when x is equal to pi over 2. So we just follow through and graph our sine function, and that's where we have a zero slope of the line tangent to the curve. At minus pi over 2, that is our absolute minimum with a value negative 1, and at pi over 2 we've got the absolute maximum with a value of 1.